Thank you. It's my privilege to be here with you again this morning. And I must say, I'm really enjoying this conference. I hope everyone else is too. I like the bit of an unusual theme that it has because it allows us to talk about things that you normally wouldn't hear about in a creation conference. I mean, to talk with a title like biological badness, I mean, where are you going to hear that, right? And I also took this as an opportunity to talk about some things that you also wouldn't necessarily hear from a physics perspective at a creation conference, and talk a bit about thermodynamics. You sometimes hear thermodynamics invoked in Origen's discussions, but it's often invoked incorrectly because there's a lot of misunderstanding associated with thermodynamics and entropy. You may have heard entropy, for example, blamed for a variety of different things, everything from the messiness of a room to death, disease, maybe even hair loss, just to pick an unrelated example. Now, hair loss, death, and disease are certainly part of the curse, but are they the result of entropy necessarily? We're going to talk about these sorts of things. And it's all related to thermodynamics. So what is thermodynamics anyway? Well, the word comes from two roots, thermo meaning heat, and dynamics refers to change or motion. So thermodynamics started out as the study of the change of heat over time. And there's several laws of thermodynamics. I'm going to focus my time this morning on two of them, the first and second laws. So let's define those briefly, and then we'll dig into what they are and how they are related to the creation versus evolution debate. So the first law of thermodynamics is that matter and energy can neither be created or destroyed. We'll talk more about that here in a bit. And the second law might be more familiar to you. This is the one that's most often invoked in Origen's discussions, is that entropy in a closed system will always increase. And if you don't know what that means, don't worry, we'll talk about that in just a moment. This one in particular is often used in Origen's, especially where it relates to the fall of man, and that ties into the theme of this conference. Many people have said that the fall of man and the curse that was placed on creation is the time when the second law of thermodynamics started operating. That was when the Lord imposed it, if you will, upon the universe. Well, there's a lot of misconceptions surrounding thermodynamics, especially when it comes to Origen's. And we see these misconceptions, by the way, in both sides of the debate, not just the Christians, but also the quote-unquote skeptics. However, if you correctly understand thermodynamics, it actually gives us a lot of interesting tools to use in this discussion. It indicates, for one thing, that our solar system is young, not billions of years old. It shows that life requires an intelligent designer. It shows that any non-creationary model of Origen's ultimately must be self-refuting. It disproves itself. It also confirms that a supernatural creator must be responsible for the universe's existence. So we'll talk about all of these here this morning. As an outline for where we're going to go with this session, we're going to start by listing a few misconceptions surrounding thermodynamics. Then we'll talk about how the first and second laws work. I've already told you what they are, but then we'll talk about exactly what they do, along with some implications for Origen's that those definitions have. Then we'll use that knowledge to revisit the misconceptions and understand why they are wrong. Then we'll dig even further and go beyond how the laws work to why they work and how that impacts Origen's. So starting out with some misconceptions. I've already told you that the second law is that entropy in a closed system will always increase. But what is entropy? A lot of people think that entropy represents disorder, and that over time, every system will always become more and more disorderly, more and more disorganized, and that reflects an increase in entropy. Now, entropy is often related to disorder, but it's not the same thing. For one thing, disorder is not a measurable value in a system. I mean, you can measure a system and determine its entropy. You can't measure a system and determine its disorder, because that's more of a human concept. It's more subjective. But this misapplication, this misidentification of entropy with disorder has unfortunately resulted in some bad arguments being used in the creation discussion. For example, Drs. Wickham and Morris in their book said that creation, or what biologists imply by evolution, actually has been accomplished by means of creative processes, which are now replaced by the deteriorative processes implicit in the second law. The latter are probably a part of the curse placed upon the earth as a result of the entrance of sin in Genesis 3, the bondage of decay to which it's been subjected by God for the present age, as seen in Romans 8. So they're saying that the second law is actually part of the curse, and the imposition of that has resulted in decay and deterioration. And that has resulted in people making arguments like this one, that's saying evolution is impossible because it represents a decrease in entropy. If entropy is disorder, then entropy increasing means things must be getting more and more disorderly and disorganized. However, biological evolution requires things to get more complex. Therefore, evolution violates an increase in entropy. However, this is a bad argument. Evolution is indeed impossible, but not for this specific reason. And we'll talk more about this here shortly. Dr. Duane Gish has, when he was still with us, used to make the argument that this fundamental law of science, talking about thermodynamics again, tells us that an isolated or closed system will never increase in order and complexity. It will never become more highly organized. Now, Dr. Gish was a brilliant man, but on this one issue, he was not correct. Because again, he's equating increasing entropy with an increase in disorder. And that, again, is not only subjective, it's giving the other side a club to beat us over the head with. And this happened to Dr. Gish a few times. For example, there was at least one debate I was reading about where his opponent in the debate allowed him to make this argument and then triumphantly held up a bottle of oil and vinegar salad dressing that he had just shaken. I said, look, this is evenly mixed, but right before your eyes, and he just held it up there, and it settled out and separated into oil and vinegar. This is an increase in order in this closed system right in front of your eyes. So this argument that Dr. Gish made is all washed up. So if entropy increasing represents an increase in disorder, then this would violate that law, wouldn't it? Well, it doesn't actually violate the law because the argument itself is being presented incorrectly. Evolutionists have also used crystal formation as quote-unquote evidence of increasing order and complexity. And some people have gone so far as to say that human growth from conception to adulthood represents a disproof of creation arguments based on this law. As this one skeptic said, can a few cells floating around in a warm liquid turn into something complex? Clearly, material can acquire complex form. Any claim that some law forbids it is a false claim. So we see if we make incorrect arguments based on entropy by not correctly understanding what entropy is, the other side is more than willing to use that against us. And by debunking the incorrect reasoning, seems to score points in this overall debate. Now, we'll talk more about these misconceptions here later. I just want to set the stage as to why this issue is important for us to talk about. So moving on from the misconceptions, let's talk about what these laws are and how they work. What is thermodynamics anyway? Well, if we start out by looking at the history of this, it's kind of interesting. It started out actually from coal mining in England in the 18th century, primarily and forward. England had an abundance of coal deposits, and as steam engines were developed, they became very useful. They could replace horsepower, or actually horses doing labor, and do so not only more cheaply, but also they could produce a lot more work. The Newcomen engine was one of the first applications of this in England. It had an efficiency of only 0.5%. A very crude piece of machinery in a sense, because 99.5% of the energy in the coal was wasted. But nevertheless, England had so much coal available to it so cheaply that these engines soon became very popular. The British economy boomed and population grew, and Britain soon began to outpace the rest of Europe, which of course the other countries in Europe noticed. And they noticed, for example, that England had all these textile mills powered by steam engines, and England was making all this money, so they wanted some of that. However, what they didn't have was abundant coal, as much as England did. They had some coal, but not as much. So they had the motivation to really dig into steam engines and how they work. We can't afford to waste 99.5% of our coal energy going out the smokestack. We need to get more work from it than the British have to do. So the scientists began to study, how do steam engines work? How can they be made to work more efficiently? And that raised more basic questions like, what is heat anyway? It's obviously vital to operating an engine, but what is it? In my talk here this morning, by the way, I'm going to use modern terminology, modern concepts. So those of you who are familiar with the history of this will understand that they thought of things a bit differently than the way I'm going to talk about them. But today we understand that heat is a result of kinetic energy, of motion. That as you heat a material more, its atoms begin to vibrate more and more energetically. And that's how heat transfers. If you have two chunks of material at different temperatures, this one's vibrating more than this one is, put them in thermal contact, and that vibration will eventually spread across so that they're all vibrating equally. Thus, they will equalize in temperature. That also implies that to transfer thermal energy from one chunk of material to another, there has to be a difference in temperature. If both chunks are vibrating equally, then they're not going to distribute the energy unequally, right? You're not going to have this one get hotter and this one get colder. They're just going to stay the same temperature. Now, this seems kind of obvious, but it has an interesting implication. It implies that small bodies will cool off faster than large bodies. Why is that? Well, imagine you have two steel balls, same material, same temperature, but different sizes, different masses. Now picture that the red represents hot material. You see, of course, that the large ball has more of it than the small one. But imagine that these are made of layers, like layers of an onion. The outer layer of each ball is going to be in contact with a cooler environment, right? And if you need a difference in temperature for heat to transfer, heat's not going to transfer from the inside, right? Because any given molecule here is surrounded by molecules of the same temperature. Only this outer layer can lose heat, right? The smaller ball, with a similar size layer, by the way, it may seem bigger, but that's an optical illusion. In the diagram, they're actually the same. You see how a higher proportion of the smaller ball is in thermal contact with the environment, therefore it will lose its heat more quickly. So why did I spend several minutes talking about this apparently obscure fact? Because it has implications for origins. If small bodies cool off more quickly than large bodies, we can apply that to the solar system. Our solar system has a variety of objects of different sizes, and the small ones should cool off from their formation more quickly than the larger ones. So if these objects were really billions of years old, the large ones might still be warm today, but the smaller ones, however, absent an external source of heat, should not be warm anymore. But many of them are. For example, our moon should have cooled off from its formation well over 1 billion years ago if the whole 4.5 billion year story for its origin were actually true. However, we have been observing gas venting from different vents on the moon, indicating apparent volcanic activity. This has been observed for quite some time, by the way. It wasn't really believed at first because it contradicts the long age idea, but evidence for this has continued to accumulate. More recently, it's been confirmed that there are active tectonic faults on the moon. This is called a scarp. It's a large fault across the moon's surface. Mapping by the LRO mission and some other things have confirmed a lot of these are associated with moonquakes, which means that they're tectonic faults, which means the moon is tectonically active, which means there's geological energy inside of it still. Even though it should have cooled off billions of years ago, it apparently didn't do that, which would indicate it's not actually billions of years old. As this author said, the whole idea that a 4.6 billion year old body like the moon has managed to stay hot enough in the interior and produce this network of faults just flies in the face of conventional wisdom. We've also observed fresh volcanic deposits on the moon. And if there's fresh deposits, that means there was volcanic activity there recently, which again was a shock to people who believe in billions of years. As this author said, this finding is the kind of science that is literally going to make geologists rewrite the textbooks about the moon. So there's a lot more we could say about the moon if we had the time to do so, but let's move on and talk about some other things. This is Io, which is a tiny little moon of the planet Jupiter. And by tiny, I mean tiny. It's only 1.5% of the mass of Earth. Such a small body should have cooled off billions of years ago from its formation. Now, it does have a little bit of geological energy imparted into it by tidal flexing, which is where Jupiter's on the one side, other moons are on the other, and there's some gravitational squeezing and flexing going on. So that does add some geological energy to the moon. However, we see violent volcanic activity going on that can't be explained as a result of tidal flexing alone. Some of these eruptions blast material 180 miles into space. Now again, there is some tidal energy being added to Io, but it's far inadequate to explain what we see. Moreover, the volcanoes are not distributed on the moon in the pattern that we would expect if tidal energy were responsible. So a straightforward look at this, being such a small body, it should have cooled off billions of years ago, but apparently didn't do that, which makes it look quite young. One of the moons of Saturn, Enceladus, pretty little moon, the brightest object in the solar system actually, because it reflects the most sunlight. I don't know if the lighting in here is good enough to see this, but these are the rings of Saturn, and here's Enceladus. Probably can't see it here, but maybe on these other screens, if you can see a little smudge below Enceladus in that photograph. Turns out that Enceladus has geysers of water and ice coming out of cracks by its south pole. Very strong geological activity going on in this little moon. Now again, similar to Io, there is a little bit of tidal energy being added to Enceladus, but it's only a couple of % of what is required to explain this activity that we see. And in fact, the activity that we see doesn't match what will be predicted if tidal energy were responsible for it. So similar to Io, a little bit of tidal energy is added to the system, but it can't explain all this geological activity that we see going on. This small body should have cooled off billions of years ago, but it hasn't done that yet. More recently, we found another example of this way out on the edge of the solar system with Pluto. The New Horizons spacecraft arrived at Pluto in 2015. Now, before the spacecraft arrived, secular scientists had expected Pluto would be kind of boring, frankly. There's several sources, several potential sources of heat for a world, and Pluto doesn't have any of them. Number one, it's small, so it should have cooled off billions of years ago. Number two, it can't have radioactive decay as a source of heat inside of it because its density is very low, therefore it can't contain much radioactive materials. And number three, it's in tidal equilibrium with its largest moon, Charon, so there's no tidal flexing going on there either. So secular scientists, believing in billions of years, predicted that Pluto would be old, cold, and dead, and interesting in some ways, but certainly would not be doing what we found that it is doing, in that it's resurfacing itself. You see these large, smooth areas here. Pluto is very geologically active. There's apparently blobs of warm material rising up from underneath, similar to like a lava lamp. Material's rising up by convection and spreading out over the surface. And the surface is very young. And how do we know that? Well, because there hasn't been enough time for any craters to be formed on it. As this scientist commented, this could be only a week old, for all we know. Now, this is completely unexpected from the billions of years perspective. This tiny little world should have cooled off billions of years ago, but it's still warm and still geologically active. As Alan Stern, who is the principal investigator of the mission, said, finding that Pluto is geologically active after 4.5 billion years, there's not big enough typeface to write that in. It's unbelievable. Well, it's unbelievable only if you come at this from a perspective of billions of years. Moving onward, let's talk a little more detail about the laws of thermodynamics themselves and see what we can get from that. The first law of thermodynamics originally said that heat can't be created or destroyed. And this has been understood for a long time. I mean, even back in the steam era, if you wanted your locomotive to move, you needed to put coal or wood or something in the furnace there and get it fired up, right? It wasn't going to move otherwise. You can't get energy out of nothing. You have to burn the coal or whatever else. Today, we've extended this principle a bit based on the understanding that matter and energy are actually different forms of the same thing. You may have heard of the famous equation E equals mc squared. This tells us that E, energy, equals m, mass, times the speed of light squared, which is a large number. So that means that energy and matter have a relationship. There's a lot of energy contained in a little bit of matter. And so the first law of thermodynamics has been extended, therefore, not just heat can't be created or destroyed, matter and energy combined is now understood to be the fullest expression of this law. This is called the conservation of matter and energy. The total amount of matter and energy combined in the universe is always conserved. It never changes. Now, you can change the relative amounts, but you can never create either one from scratch. So if you want energy, you have to get it from matter. You know, if you want your locomotive to move, to have kinetic energy, excuse me, you need to burn some matter. You need to convert that matter into energy. And we can convert actually in both directions. So the most efficient way we know how to convert matter to energy is in a nuclear explosion. I mean, a little bit of physical stuff converts into a large amount of energy, right? We can go the other direction too. We can convert a lot of energy into a little bit of stuff. And we do that in particle accelerators. We get tiny chunks of matter zipping around at close to the speed of light and smash them together. More stuff comes out of the collisions than went in. Not just the number of particles, but the amount of physical stuff. Now, are we creating matter from nothing? No. We're converting the kinetic energy, the energy of motion, into that matter. So you can get energy from matter, you can get matter from energy, but you can't create either one from scratch, because that violates this very fundamental law of physics. And we even experience this law in our everyday lives. I mean, think about this. Why do you need to eat food every day? Regardless of how difficult that process might be sometimes. Well, because your body needs energy to function, can't make it from nothing, because that violates this law of physics. So you have to get it from the chemical energy stored in the food after you successfully get it into your mouth. Why do you get a bill from the power company every day? Well, not every day, excuse me, every month, or whatever it is, because your appliances need energy to operate, can't manufacture that from nothing, you can't pop into existence from nothing because that violates physics. You have to get it from an external source, the power company, which also can't make it from nothing because that violates physics. It has to get it from the chemical energy stored in coal, or the gravitational potential energy in flowing water, or the solar energy from the sun, which also can't make it from nothing because that violates physics. It has to burn hydrogen or helium or whatever. On and on it goes. This is a very fundamental principle in physics. In fact, you couldn't be watching this presentation here this morning if it weren't for this law, because some of the principles of circuit design are based upon it. As one of my textbooks points out, conservation laws are the guiding principles of physics. These are absolute conservation laws. They are always obeyed. And again, I'm emphasizing here how fundamental this is to physics. And this has implications for origins. If you ask some of the big questions, like where did our universe come from? Well, some people will tell you that it came from nothing. That there was nothing, and then there was a fluctuation, and then the universe popped into existence. In a different form than it is today, but still, something had to come from nothing. Does this law of physics, the first law of thermodynamics, allow for that to happen? No. This is a violation of that law on the largest possible scale. Now, interesting, if you ever take a physics class and you answer a homework problem or a test problem in a way that contradicts this law, then it's wrong. You know, the way that it's wrong may vary depending on what you did, but it's going to be wrong nonetheless. Yet here's an entire worldview based on a violation of this very fundamental principle. Everything could not have come from nothing because nothing can come from nothing. You can't get anything out of nothing. So the first law of thermodynamics actually disproves this entire category of cosmogonies, of histories of the cosmos. Any cosmogony, any proposed history for the universe that relies upon something coming from nothing is not allowed by this law of thermodynamics. Moving onwards, we have the second law of thermodynamics. Entropy in a closed system will always increase. Well, what is entropy? This author defines entropy change as the measure of how more widely a specific quantity of molecular energy is dispersed in a process. So in other words, entropy increases as energy spreads itself out. And this is, again, something that we experience in our everyday lives. Let's say you want to have a fire in your fireplace. You start out with a piece of wood. Now, you can hold a piece of wood in your hand. All the mass energy represented by that wood is concentrated in one piece. What happens when you put it into the fireplace and ignite it? That matter now converts itself into heat, some of which comes into your living space, some of which goes up the flue into the atmosphere and then radiates out into space eventually. Some of it converts into light that comes into your living space. There's kinetic energy, the motion that the air winds up doing. There's particulate matter, smoke and such, going out the flue, etc. What started out with the concentration of mass energy that you could hold in your hand now is dispersed into your room, into the area outside your window because there's radiation going that way, out in the atmosphere, even out into space. Point is, it's dispersing, right? And once it's dispersed, by the way, there's no way to get it back either. So the second law basically says that energy will, as a process happens, will always be dispersed and distributed over a larger area, over a larger volume of space. So this has an important implication. It implies that hot things cool off. Well, there's a brilliant insight, Spike. We're so glad we came to this talk this morning. No, wait. This is actually good stuff. This has implications for origins too. For example, it allows us to use hot things as a crude form of clock. What do I mean by that? Well, let's say you walk into a room and there's a hot cup of coffee sitting on the counter. How long has that coffee been there? A long time or a short time? Short time. Why? Because it's still hot. There hasn't been enough time for it to cool off. Could it have been there forever? No, why not? Because had it been there forever, it would have cooled off forever ago. Let's apply the same logic to the cosmos. Is there anything in the universe that hasn't cooled off yet? Stars. They will cool off over time, right? They will consume all their fuel, they'll burn out. Some will explode before they do that. But one way or the other, every star has a limited lifespan and will go away eventually. So if the universe had been here forever, all the stars would have been gone forever ago. The energy represented within them would have distributed itself through the universe, so the entire universe would be a few degrees above absolute zero, as would everything within it. Everything would be the same temperature, and everything would be dead, by the way. But that hasn't happened yet. Now, some people argue, well, wait a minute, new stars can form. There's actually problems with that from a secular perspective, but setting that aside, star formation still requires energy, of which there's a limited amount available, so that too would have been consumed forever ago if the universe had been here forever. So the fact that the stars are still there, and that even star formation will eventually run out of energy, tells us that the universe can't be eternally old. It can't have been there forever because the stars are still there. And this is related to origins in a couple of ways, actually. There are some Christians who teach that we need to embrace the Big Bang model because it shows that the universe had a beginning, and that's what Genesis says. Well, as other speakers have already pointed out, Genesis is actually not compatible with the long-age models in the first place. But my point here today is that we don't actually need the Big Bang model to prove that the universe had a beginning. Thermodynamics gives us that. If you want to prove that the universe had a beginning, walk outside and look up. Do you see the sun during the day? Do you see stars at night? If so, the universe is not eternally old, which means it must have had a beginning. It's existed for a finite amount of time. And the sun and stars are a daily reminder of that. So we've talked about how the first and second laws work. Now we're a little bit better equipped to go back to those misconceptions and clear some of those up and understand why they're wrong. So the idea that evolution is impossible because it represents a decrease in entropy, well, the Earth isn't a closed system. So that means that the second law can't be applied to it in isolation. So in theory, because the Earth is receiving energy from the sun, entropy could, in theory, decrease here on Earth as long as it increases overall in the larger system. Now again, I'm not saying evolution happened or that it's even possible. I'm just saying that this is an invalid argument to use against it, and so we shouldn't use it. What about oil and vinegar separation? Is that a reversal of entropy? No, it's not. Actually, if you look at the chemistry going on here, entropy increases as that separation occurs, but because sometimes people incorrectly identify entropy with only this vague concept of disorder, they get confused on that. Crystal formation also represents an increase in entropy if you look at what's happening, and certainly growth is not a violation of entropy either. What about the subject of our conference here, the fall of man and the curse that resulted from that? Is that the source of the second law of thermodynamics? I'm going to argue no, because there are things that presumably existed before the fall that, according to our current understanding at least, reflect the operation of this law. For example, digestion. Had Adam and Eve not fallen, could they have eaten the fruit available to them in the garden? Sure, and presumably they could have digested it, right? Well, digestion operates according to the second law. Entropy is increasing during that process. That would indicate, therefore, that the second law was in operation before the fall happened. We know Adam and Eve walked in the garden before the fall. Well, walking requires friction. There has to be friction between your feet and the ground, otherwise you'd be like on an ice skating rink or something. There's no indication that happened for them. Well, friction represents an increase in entropy. That's the second law in operation again. So again, the second law was apparently operating before the fall. Therefore, what was it that changed when the curse was imposed? The Bible doesn't tell us specifically. My personal opinion is that the Lord removed divine sustenance and divine provision from the creation at that time. And an example of this is the Israelites during the 40 years in the wilderness. I mean, they were walking around in the desert. There was friction between their sandals on the ground, right? Because they were able to walk. Yet, nevertheless, their sandals did not grind away as a result of that process. I mean, the second law was working. Produce friction by rubbing your hands together. You feel heat, right? That's the second law. Well, second law was in operation for the Israelites, but nevertheless, the deterioration, the physical impact of that on their clothing and sandals was prevented by the Lord's divine sustenance. So my personal opinion, and I'm saying it is just an opinion because the Bible doesn't tell us one way or the other, is that what happened at the fall was the Lord removing his, shall we say, his shepherding of our physical well-being and allowing our bodies to receive the full implication of what happens in the physical universe. So that clears up some invalid arguments from thermodynamics. We've talked about some valid ones based on the first and second law. Let's add a few more. Thermodynamics actually raises issues for origin of life research if you come at this from a perspective that denies a creator. For example, life is made of proteins. Proteins are made of amino acids. Amino acids have a property called chirality, where they come in two forms, left-handed and right-handed. Now, interesting because amino acids in life are all the left-handed variety, whereas sugars, and DNA is partly made up of sugar, for example, sugars, are right-handed. So if you want to say that life came from a pool of warm chemicals or whatever, you have to first of all explain how the amino acids can form from these chemicals on their own without a creator. Then you have to somehow separate out all the left-handed amino acids from the right-handed ones so that the left-handed ones can be the exclusive source that life formed from. And interesting because even if you somehow separate these out in the laboratory, so you have a little pool of only left-handed ones, left to their own devices, because of thermodynamics, they will revert back to an equal mixture of left and right. So thermodynamics actually raises problems for people trying to explain how life could have formed from non-living chemicals without a creator being involved. Thermodynamics also has a role to play in DNA because DNA will degrade over time. Our bodies actually spend a lot of effort, if you will, repairing DNA constantly. But one of the things that happens when an organism dies is it stops repairing its DNA. So DNA starts to degrade without being sustained anymore. And it turns out that DNA is fragile enough that even if you freeze it and seal it off from air so that oxygen and oxidation can't happen, the base pairs in the DNA strands will still spontaneously break over time. And again, this is for thermodynamic reasons. This study found that even under these conditions, like I said, frozen and sealed off from air, every base pair will have broken in the DNA strand after 6.8 million years. Now that's interesting because that's almost exactly 1/10 of the time that the oldest dinosaur fossils are supposed to be. And as Dr. McLean mentioned, there's evidence of DNA in dinosaur fossils. So DNA can't be there after 6.8 million years, and that's if it's frozen and sealed off from air. And of course, a fossil buried in the hillside is neither of those, so presumably it will degrade even more quickly than that. And of course, with Dr. McLean here, you don't need to hear from me about dinosaurs, but I wanted to mention there's actually specific reasons why this is happening and how it creates numerical, quantifiable problems for those who want to believe in the millions of years. The first and second law, of thermodynamics combined also is useful to us because it creates something that I like to call the secular dilemma. And sometimes people ask me, how do you get conversation started with people who don't share your creation perspective, who's an atheist or whatever? And this is one of my favorite ways to start because it's a simple question, 6 words. Ask the person, did the universe have a beginning? How many possible answers are there to that question? 2. There's yes and there's no. So either yes, there was a beginning, or no, there wasn't a beginning, in which case the universe has always been there. In other words, the universe is eternal. Every model of origins has to have an answer to this question built into it, right? If you're going to talk about where the universe came from, you have to pick one of those two answers at the foundation of your model. Thermodynamics will cause problems for you, though, if you come at this as an atheist who denies a creator, because both of these problems run afoul of thermodynamics in a different way. For example, if you try to say, yes, there was a beginning, okay, so if the universe had a beginning, and the universe is everything that exists, that means everything that exists had a beginning. What could have existed, therefore, before that beginning? The answer is nothing, right? Because if there was something before the universe began, then whatever began wasn't actually the universe, because the universe is everything. Still with me? So, if the universe is everything and the universe had a beginning, then before the universe began, there could have been nothing. So if you're going to build a cosmogony, a history of the cosmos, and you want your answer to that question to be yes, the universe had a beginning, then here's a graphic of what existed before the universe did. Of course, that's only in our misconception. But ask the question, can nothing actually make everything? Can nothing make anything? No, because nothing can create nothing. Nothing can do nothing. From nothing comes nothing. This is a direct result of the first law of thermodynamics, right? Conservation of mass energy. You can't create mass or energy from nothing. So this law of thermodynamics tells us something could not have come from nothing, which means the question of did the universe have a beginning, the yes answer is incorrect. Well, what about the other option, the no answer? The no answer says the universe is eternal. Well, what did we talk about a moment ago with the second law of thermodynamics? We saw that the universe can't be eternal, right? It can't have been there forever because heat energy is still unevenly distributed. There's still very hot stars sitting in the middle of very cold space. If the universe had always been there, that would no longer be the case. Since it is still the case, the universe cannot be eternal, but that was the only other option open to the atheist. You see the problem here? The atheist has to pick yes or no. Those are the only two available answers to the question. Each answer violates physics in a different way. Any secular model of origins has to pick one of those two answers, yes or no, but you can't have either answer be consistent with known physics. Each answer violates thermodynamics in a different way. Because the first law of thermodynamics tells us the universe can't have had a beginning, therefore it must be eternal. Whereas the second law says it can't be eternal, therefore it must have had a beginning. You see the problem here. So any atheistic history of the cosmos is not allowed by thermodynamics. Whichever of those answers you choose, you're going to violate physics one way or the other. Only a supernatural creator can explain the universe in a way that's consistent with physics. Yes, the universe had a beginning. We know that because uneven heat distribution still, but it did not come into existence by itself. There's a supernatural creator outside of physics that is responsible for our universe. Because ultimately there's only three possibilities. Either the universe was formed by a creator, or it formed by itself without a creator, or it never formed, it always existed. The first law of thermodynamics doesn't allow formation without a creator. The second law doesn't allow it to always have existed. The only remaining logical option is that a supernatural creator is responsible for the universe, and that's the only explanation consistent with physics. So this is a great conversation starter, by the way. Simple question, short, easy to remember. Everybody understands there's only two possible answers, and then you can walk them through the implications of both of those answers without a creator being involved. I would also argue, by the way, this is just my personal opinion again, that this is evidence of God's grace. God could have created the universe any way he wanted. He could have created it in such a way that it looked potentially like it came from natural processes and told us just to believe by faith that he did it because he said so. He could have done that. It would have been within his right to do so. But he didn't do it that way. It interests me that the Lord created the universe in such a way that it operates according to laws that demonstrate he's responsible for it. because perhaps he knew that in our weakness that we would benefit from such a thing. So we talked about misconceptions and some valid arguments. We talked about invalid arguments and valid ones. Now let's move on. We've talked about how the laws of thermodynamics work. We haven't talked about why. In particular, the second law of thermodynamics. Why does entropy always increase? Well, in the latter part of the 1800s, scientists began to wrestle with this, especially this man here, Ludwig Boltzmann. You'll see his name appear again in just a moment. And there's an entire branch of physics called statistical mechanics that deals with this, and there's a lot of math, but let's deal with some simple concepts. Let's talk about dice, because this is something we have experience with. Let's say that we're going to roll some dice, and each die represents a single calorie of heat energy, okay? And let's say that the number on the die, when we roll it, tells us where in this room the calorie is, which part of the air is being heated by that calorie at that moment. So let's mentally divide up this room into 6 regions. We'll do like top to bottom, so there's a top half and a bottom half, and then we'll divide it in thirds this way. So we have 6 regions total. There's region 1, region 2, 3, 4, and then the back is 5 and 6, okay? So each die represents 1 calorie, and the number on the die tells you where in the room the calorie happens to be at that moment. Now remember, air molecules are always bouncing around, and they're exchanging heat energy with each other. So the calorie could, in theory, move around. Calories could move around. Now, if there's only 1 calorie in the room somewhere, we could figure out where it is. We could represent its location, rather, just by rolling a die. Now, my point here is that with only 1 die, only 1 calorie to deal with, it could equally be in any region of the room with the same odds of being there, right? Because you roll 1 die, you're going to get a 1 through 6. There's equal odds of getting any of those numbers. So if you only have 1 calorie, there's equal odds of it being anywhere in the room. This will be relevant. Just bear with me. What if there's 2 calories? Well, again, if they're moving around at random, 2 calories, when you look at their possible locations, there's a lot of different combinations now, a lot of different arrangements of these 2 calories in the room. Now, there's 6 possible arrangements where both calories are in the same region, okay? But there's 36 possible arrangements. So only 6 out of the 36, or 1 out of 6 odds, represent the odds of both calories being in the same place, okay? 3 calories, the odds of them all being in the same place, reduces down to 1 out of 36. 4 calories, the odds of them being in the same place are 1 out of 216. 5 calories, 1 out of 1,296, and on it goes. You see how the numbers are increasing drastically. The more calories there are, the greater the number of possible arrangements. With only 16 calories of energy in the room to track, there's 2.8 trillion possible arrangements for them to be in. Only a handful of those possible arrangements represent all the calories being in one spot. So why am I saying all this? Well, the more calories you have to deal with, the more extreme the odds are against them all being in the same place. That's why this room is more or less all the same temperature. Slight variations here and there. But in theory, all the heat energy could be in that corner, so it's boiling hot in that corner, and we're all sitting here with icicles out the ends of our noses. But that's never going to happen. Why is that? Because there's so many calories of heat energy in this room, the odds are whatever arrangement they wind up in, moment to moment, is going to be one of those where they're all evenly distributed. I hope I haven't lost anybody yet. I'm pretty sure I have, though. But here's why this is important. Because as the system gets large enough and you're dealing with large enough numbers, the odds against these specific arrangements becomes insurmountable. This is why the second law works. This is why heat energy, and actually energy in general, will always distribute itself through a system over time. Because the number of arrangements where the energy is all evenly distributed far, far outnumber the few arrangements where it's more concentrated. Does that make sense now? Another way to look at this, if I take a deck of playing cards, I just got it from the store, open it up, the cards are all ordered ace through king and 4 suits, right? Shuffle, 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 so they're all mixed. Now I have an evenly mixed deck of cards, If I shuffle them again, what are the odds of it returning to that initial ace through king and all four suits that it started in? You're never going to see that in your lifetime, shuffle once a second until you die, right? Why is that? Because a deck of cards has 8 times 10 to the 67 possible arrangements. Only one of them represents that initial order. So if you're shuffling and you're going to wind up at some new arrangement at random, your odds of hitting that original one is 1 out of 8 times 10 to the 67, which is never going to happen. So what's the point, Spike? Why did I talk about all this? Because we can use this reasoning to calculate the probability of any given arrangement of matter and energy. All the heat up in that corner is very unlikely compared to all the heat being evenly distributed because there are so many other ways for it to be arranged equally compared to everything being up there. If we apply that to the whole cosmos, and we recognize that a low entropy configuration where all the heat energy is concentrated is much less probable compared to a high entropy configuration where it's all distributed, well, we can apply this to the Big Bang model. We can calculate the Big Bang model's expected entropy for the universe that it supposedly created. And guess which of the two options, low entropy or high entropy, the Big Bang model can produce? I shouldn't use the word can because it implies it can do anything, but given the Big Bang's own reasoning, which configuration of the universe would it have produced? The answer is a very low entropy universe. In fact, if we look at the universe today, it's in a very low entropy arrangement. Now, I told you a moment ago, we're not going to have all the heat in the corner and be freezing cold out here, right? Isn't that kind of how the universe is? You have very hot stars punctuating vast expanses of cold space. This is an extremely low entropy arrangement of matter and energy, and thus a very low probability arrangement based on that dice illustration, right? Furthermore, if the universe has been here for almost 14 billion years, if it's low entropy today, and if entropy always increases over time, that means it was even lower in the past, and even less probable in the past. So even if something could create itself from nothing, which is obviously impossible, we talked about that, the first law of thermodynamics doesn't allow that, even if something could create itself from nothing, our universe is extremely unlikely to have been the result of that process. Here's an analogy, and this may seem kind of weird, but hopefully it'll make sense. Let's say a friend came to you and said, you know, I just figured out this interesting model of origins. I've created a model that says the city of Washington, D.C. came out of nothing. There was nothing, and then there's a fluctuation, and the whole city popped into existence, complete with the people and government officials and the buildings and everything else. And you say, well, no, something can't come from nothing. Well, I think it can, though. Well, even if something could come from nothing, you wouldn't expect something as complicated as an entire city to pop into existence. But your friend argues that it can. So to illustrate to your friend how silly this idea is, you say, well, let's think of something within the city. Like there's the National Archives building where the US Declaration of Independence is stored, right? If something could come from nothing, it is far more likely that only the US Declaration of Independence popped into existence, complete on the original parchment with the signatures and all the rest of it, compared to the entire city surrounding it popping into existence too. Now, turning into a weird talk here, isn't it? As silly as that idea is, it's still much more likely than an entire city popping into existence, right? And the same reasoning applies to the Big Bang model. The Big Bang universe is so improbable, so unlikely, that if something actually could pop into existence, it wouldn't have been the Big Bang universe. It would have been something else that was more probable, one of which is called a Boltzmann brane. This is called the Boltzmann brane paradox. It is the idea that the universe didn't pop into existence from nothing 14 billion years ago, because if you calculate the odds, it turns out it's much more likely that only a single brane popped into existence. Yours. Because you know you exist, right? You know, the rest of us are kind of suspect, but you know for sure you exist. So the Boltzmann brane paradox says that instead of the Big Bang actually producing a universe 14 billion years ago, it's much more likely that your brain alone popped out of the void a few seconds ago complete with false memories of living a life up until now, because that's just how the molecules in your brain happen to be arranged. Complete with an illusion, by the way, that this world around you is real. You're not really in this room right now. It's all part of the illusion. Not that any of this matters, because your brain is about to fluctuate back into the void in just a moment anyway. But this is actually what the math of the cosmological models say is much more likely than the Big Bang happening. As this article said, it could be the weirdest and most embarrassing prediction in the history of cosmology, if not science. If true, it would mean that you yourself are more likely to be some momentary fluctuation in a field of matter and energy out in space than a person with a real past in an orderly star-spangled cosmos. Your memories and the world you think you see around yourself are illusions. This bizarre picture is the outcome of a recent series of calculations that take some of the bedrock theories and discoveries of modern cosmology to the limit. The basic problem is that it's hard for nature to make a whole universe. It's much easier to make fragments of one, like planets, yourself maybe in a spacesuit, or even, in the most absurd and troubling example, a naked brain floating in space. Nature tends to do what's easiest from the standpoint of energy and probability, and so these fragments, in particular the brains, would appear far more frequently than real full-fledged universes, or than us, or they might even be us. Alan Guth, cosmologist at MIT, who's a rock star among cosmologists, by the way, who agrees this overabundance is absurd, pointed out that some calculations result in an infinite number of free-floating brains for every normal brain, making it, quote, these are his words, infinitely unlikely for us to be normal brains, unquote. So here's one of the most prominent cosmologists in the world today admitting that these cosmological models say the universe isn't real because it's infinitely more likely that you're just a naked brain floating in space. So getting back to our analogy, hopefully this will help if you're still uncertain about what all this means here. This is like the friend saying the city of Washington, D.C. popped into existence, and you say, that's ridiculous. It's actually much more likely that only the Declaration of Independence popped into existence. That's still a silly idea, but it's still billions of times more likely to have happened than the entire city. Similarly, the Big Bang model is so mathematically unlikely that even a ridiculous idea like a brain popping into existence is far more likely. Called the Boltzmann brain paradox because this is based on the same mathematics that Ludwig Boltzmann discovered earlier. And just to clear things up, by the way, the math doesn't say that you're a naked brain floating in the cosmos, because there is no cosmos. It's just you. And I know what you're thinking by this point in the presentation, and the answer is no. No, Spike isn't making this up. This is actually a real problem in secular cosmology today. As this paper points out, a typical observer in the multiverse is a Boltzmann brain. In the eternally inflating vacua, observers are infinitely more likely to be Boltzmann brains than honest folk like ourselves. This paper says that the most likely fluctuation consistent with everything you know is simply your brain, complete with quote-unquote memories, fluctuating briefly out of chaos and then immediately equilibrating back into chaos again. This is sometimes called the Boltzmann brain paradox. And there's a variety of papers on this, avoiding Boltzmann brain domination in holographic dark energy models, a note on Boltzmann brains, sinks in the landscape Boltzmann brains and the cosmological constant problem. Can the Higgs boson save us from the menace of the Boltzmann brains? Boltzmann brains and the scale factor cutoff measure in the multiverse, etc. And a while ago, by the way, they thought they had solved this problem, but then realized the calculations were wrong, and so this paper was published, The Return of the Boltzmann Brains. Now, I had to dig deep into the cosmological literature to find this stuff, because cosmologists don't like to talk about this. I mean, would you? Because when you look at the math, and you have to decide between what does cosmology really predict, a universe or just a brain, the brain wins every time. So what does this mean? The Big Bang model predicts that you're a Boltzmann brain that's infinitely more likely, quote unquote, than this being a real cosmos according to their worldview. So if you're just a brain, then there was no Big Bang, and there's no universe. And if there's no universe, there's no beginning to the universe. So the Big Bang never happened. So if the Big Bang model is true, then the Big Bang never happened. So the Big Bang model ultimately disproves itself. Sometimes in the creation evolution debate, Christians tend to feel defensive especially when the other side is using arguments like you're just using God of the gaps and all the rest of it. No, the science is on our side on this. The atheist may think that science and cosmology gives him a weapon to use against Christianity, but in reality, the only weapon it gives him is this one. So, brief review of what we talked about. We talked about bad arguments that we shouldn't use, like the idea that evolution being impossible because it violates second law of thermodynamics. We talked about whether or not the fall of man is responsible for the second law of thermodynamics being imposed on the created order, and I argued no, because there's things at play in the Garden of Eden that rely upon it, and I believe personally that before the fall, the Lord suspended, if you will, the harmful effects of it on us. We talked about some bad arguments that can happen if you mistakenly conflate entropy with disorder, and how those arguments are actually misconceptions. We talked about the first law of thermodynamics, that matter and energy can't be created or destroyed. The second law, entropy will always increase, hot things always cool off. We talked about some interesting implications of that, like objects in the solar system looking very young, like origin of life scenarios being impossible, like DNA and other reasons to believe that things that are claimed to be old are actually quite young. Then we talked about the Boltzmann paradox, which to me is really the ultimate absurdity of the secular worldview in general. And I think it's interesting that really this whole thing started with all these interesting implications for origins out of a commercial motive. There were Europeans who wanted to make as much money as the British were making. So they started to figure out how they could make better and more efficient engines. And ultimately, the knowledge that this has produced has given us some interesting insights on origins. And out of this whole talk, the one thing that I'd like you to have as a takeaway, and you might be wondering, what do you mean takeaway, Spike? This is supposed to be a creation talk. You started out talking about coal mining in England, and you wound up with naked brains in space. What are we supposed to take away from all this? Well, it's this one item here, the secular dilemma. I like this as a conversation starter with people because, simple question, did the universe have a beginning? 6 words, easy to remember. Everybody understands there's only 2 possible answers. And hopefully the problems with each answer from a secular perspective are easy to remember. If there was a beginning, then something had to come from nothing. We know that's impossible. If there wasn't a beginning, then everything had to be eternal. We know that's not possible either. The only answer is that a supernatural creator has to be responsible for the universe. And what do you think about that, Mr. Skeptic? And that's said in a nice way, by the way. That's not a challenge. As I said, this is a conversation starter. This isn't a gotcha. This is just a question you can ask to get people thinking. You're not going to change someone's thinking overnight, but give them something to chew on long enough, and maybe something will come of it. And by the way, this question here is what started me on my journey from atheism to Christianity. It wasn't worded quite in this way, but it's ultimately what it came down to. So that is the end of my talk. Thermodynamics does indeed confirm creation. My site, as Zach mentioned, is creationastronomy.com, and I've reached the end of my time, which is good because it's the end of my talk. So thank you again for your time and attention, and my privilege to speak here.